So here for chapter 7, like I said, the last thing we did after this concept question, if you remember, was elastic collision. Now we decided to drop elastic collision. It will not be included in the midterm. Instead, we're going to include this part. So work done by non-conservative forces and other forms of energy. And there's an example applied to work, energy, and power in the human body. Okay, so these are the two slides we're considering, okay, for the midterm. Okay, so there's going to be a question related to this part instead of elastic collision, which is more relevant to you guys as medical students. Okay, so starting with this one, we're saying work done by non-conservative forces and other forms of energy. Okay, now when there is non-conservative forces such as friction, okay, such as friction, air resistance, and other forms of energy that does not come under the mechanical energies. Okay, now the law of conservation of mechanical energy does not hold. Now the law, like we saw it previously, okay, so the conservation we saw where kinetic energy plus potential is constant. This does not work anymore. Why? Because we still need to include, okay, the contribution from the non-conservative forces in the form of work done by those forces, and also eventually by some other energies. Now, how do we include that? First, I would say that kinetic energy, okay, that's what the KE stands for. So the KE stands for kinetic energy. Use red. KEI, so which means all the kinetic energy involved, plus all the potential energies involved, okay, is equal to, or sorry, not all. So we're talking about initial here. So that's what the I stands for. Yeah, sorry about this. So initial here, okay, so we're talking about kinetic energy initial plus potential energy initial, okay. Now we need to include all the other energies, okay, that come into the system. And we're going to use this notation, OE, which stands for other energies, okay, initial, and then plus the work done by the non-conservative forces. Okay, so the work done by the non-conservative forces, this is initially. Now on the other end, okay, in the final state of the system, this is the initial state. And on the other side of the equation, you have final state. Okay, this is final state. Then you have kinetic energy final plus potential energy final plus other energies final. Okay. Now this is then work done, okay, taking into account non-conservative forces and other forms of energy. Now as an illustration, we're going to apply this to the work, energy, and power in the human body. Now we have energy, okay, or other energies. Now here in the form of food energy, okay, other energy in the form of food energy will go, okay, this is in the initial state. Okay, so this is in the initial state. Will go into the final state as thermal energy, of course, if you're doing an effort, etc. So this will turn into heat, thermal energy. Now, whatever food energy that is not consumed, that is not burned, of course, will be stored as fat. So this is then the other forms of energy in the final state. Okay, so this is food that goes into the body. Okay, so this is food that goes into the body. And this is what you get. This is in the initial state, of course. In the final state, so the food will end up either being consumed, burnt, producing thermal energy, and then stored as fat. Now, of course, this food will serve, okay, to produce some work, effort, okay? Now, this work here, we call WNC, a non-conservative work. We're saying it is negative. Why is that? Because in this case, the work is done by the system. It's by the human body. Okay, so the work is done by the human body. Remember, when we say work done, when work is done by the system, when work is done by the system, so we say, so this is work done by the system, the work is negative. Okay, so we take it as negative. When work is done on the system, the work is positive. Okay, so this is something we discussed last time. So we can write this in the following way. So this is other energies in the form of food that goes in. This is initial. Okay, and then here, of course, you include the work done by the body. Now, this is going to be a negative work, is equal to other energies final. Again, other energies could be either thermal energy, could be either something that is stored, okay? With no change, we're saying in mechanical energy, okay? So with no change in mechanical energy. Now calculate, for example, we'll try to apply this quickly. One second, please. So here the example says, if a person who normally requires an average of 12,000 kilojoules, that corresponds to 3,000 kilocalories of food energy per day, consumes 13,000 kilojoules per day, he will steadily gain weight, okay? Now, how much bicycling per day is required to work off this extra 1,000 kilojoule? Now take the energy consumption rate when cycling is 400 watts, okay? Now again, we're talking about a normal person, okay, requiring 12,000 kilojoules, okay, as food energy, and then consumes 13,000 per day. Of course, if the person only needs 12,000 and consumes 13,000, we have an excess, an extra of 1,000 kilojoule. Now, this extra 1,000 kilojoule, okay, that goes in, of course, if it's not burnt, will be stored, and it will be stored as fat. Now, we're asking you, how much bicycling per day is required to work off this extra 1,000 kilojoule? And for this, we want you to take the energy consumption rate when cycling here is 400 watts. So what does that mean? The consumption rate, if you remember, and it's given in watts, 400 watts. The consumption rate Yes, Alia. Yeah, that's fine, Alia. So I'll fix this later. And if you give me a couple of minutes, just yeah, like I said, I will drop an email to the 2 or 3 students who used to attend. Just give me 2-3 minutes, please, and then we carry on. So in the meantime, if you can think about this question and how we can solve it, just give me 2 minutes time. Now let's resume then. And like I said, for those of you who did not manage to take the attendance, I'll take it at the end. Just remind me, please, at the end. So again, the idea here is to consume this extra 1,000 kilojoule, okay, to burn them, considering that, and how do we intend to burn them? By cycling. So I'm looking for the amount of time required, okay, for cycling in order to burn these 1,000 kilojoules. Now, how are we going to do this? First, the consumption rate, we're saying the consumption rate is 400 watts, which means what? What is the consumption rate? It corresponds to the power. Very good, Ranim. So the power, we defined it as work done over a certain period of time, delta T. So work done is an energy, right? Divided by a time, this will give you power in watts. Now that means if I want to burn this much energy, the 1,000, okay, kilojoules. So all I need to do then, considering I know the power, so all I need is to use this same formula to calculate delta T, and now delta T will be equal to the amount of energy, W, divided by the consumption rate, which corresponds to the power. Now, delta T then, delta T will be equal to 1,000. Now, it's in kilojoules. Now, in a question like this, we are not using kilojoules, but we're using the joule. Okay, so that will have to be multiplied by 10 to the power of 3, or 1,000, divided by the power, which is 400 watts. Now, already you can eliminate these two zeros, and the 10 times 1,000 is 10,000. Okay, so this is 10,000 divided by 5, sorry, divided by 4, divided by 4, and this will give us 2,500 seconds. 2,500 seconds. So this is the amount of time, okay, training required to burn this 1,000 kilojoules. Now, of course, if you want the time in minutes, I know it's less than an hour, because 1 hour is how many seconds? Can you remind me? So in 1 hour you have, very good, Fatima, Hannah, Faiza, yes, 1 hour is 3,600 seconds. So I know I am dealing with less than an hour. Okay, so 2,500 is less than an hour. So how many minutes is that? I would say, how do we convert? Yes, Ranim, that would be 41.67. And you got that by dividing the 2,500 by how much? So we divide this by the 60. Very good. And you end up with something, like you said, Ranim, 41.67, or you can round it. We're not going to argue about seconds. So it's about 42 minutes. So 42 minutes of training then are required to burn this 1,000 kilojoules, okay? Right, so that's all for chapter 7. Again, we decided, again, for those who joined in late, so we decided to drop the elastic collision, and we're including this part in the midterm. Now, let me take you to midterm from 2008, okay? And then we can start the review again. So 1 second. So open it from the lecture. Now, can you see the questions, guys, from the slides or from the PDF? Yes. Yes, Faiza, inelastic collision is still included. So yeah, inelastic is still going to be there. Okay, so we're just forgetting about elastic. Okay, just forget about elastic. Right. Okay, I'll send an email just to remind everybody we're doing this. Now, some of you also have sent emails about questions related to homework, which were either challenging or they were suspecting an error, etc. Now, I will come back to those, okay, maybe on Thursday or eventually in the recordings I'll be posting, sharing with you guys, okay? So don't worry if you feel you had issues with some of questions or questions have not been clear. If I did not reply to you by email, okay, if I did not reply to you by email, so you'll see the answers either in the recordings or I'll get back to you hopefully shortly, okay? So the first two questions we've already covered, okay? The Iron Man, if you remember, so we already talked about this when we covered this part. Also question number two, we already covered this one. Now the ones we did not cover are starting from question three, okay? So from question three onward. Question from Ran, are we going to have another review session today? Now, like I said, Ran, what I'll do, I'll post a video recording, okay, to review some of the questions, right? So if you have any question, please do let me know, all right? So I'll include. Of course, we'll be halfway through this midterm 2018. And what we will have left will be 2017 and 2016, okay? Now, I'll probably post 2017 this afternoon, okay? And then we'll have only 2016 left. If you have any other questions, okay, related to any question, just drop me an email, or we can arrange for a suitable time before that, okay? No bonus questions. We will see about that. We'll see about that. Usually we have bonus questions, maybe a question or two. We'll see about this midterm. Now let's start without further delay with the questions. Now starting with question three, a truck is moving, okay, with constant velocity on a level road and has a crate in its cargo bed, okay. Now the truck suddenly slows down. Which of the following statement is true regarding the motion of the crate? Now we're highlighting already the answer, the correct answer, which says the crate slips forward because the friction force from the cargo bed is not large enough to keep the crate moving with the same backward acceleration as the truck. Now for questions like these, it's better to draw a quick schematic, okay, of the system. Now, it's just a simple schematic, but it can really help. So, for example, the truck with the crate like this on its cargo bed at the back. Now we're saying the truck is moving first with constant velocity. So velocity is to the right, for example. And then the truck suddenly slows down. Now, when it suddenly slows down, where is the acceleration? Can you tell me? When it slows down, acceleration will be, I'm sure you will all agree, going backwards. Tanya, Anim, very good. This here. So acceleration will be pointing backward. Now, here, if the trach wants to slow down, what will the crate want to do? So the crate will want to continue forward. Yes, Ranim, that's inertia. Okay, so just imagine yourself standing up here. Okay, and see what happens and feel what happens if the truck slows down. Of course, your body will want to move forward. Now, so the body or the crate will want to move forward like this. Now, of course, if the friction is not enough friction here between the crate and the cargo bed, if the friction is not large enough, of course, the crate will slip forward. Now, that's what we see. We're saying that the crate slips forward. Okay, the crate slips forward. because the frictional force from the cargo bed is not large enough to keep the cargo from moving in the same backward, with the same backward acceleration as the truck. So we know the acceleration is backward, okay? We know it because the truck is slowing down, okay? And in this case, if there's no friction, the crate will move forward. Now, we're not accepting option A. Option A says the block slips forward to conserve the momentum. In this case, it's not true. We're dealing with non-conservative forces. There's a force acting on the truck, an external force, okay? Which means net force is not equal to 0. The crate slips backward because the frictional force from the cargo bed is not large enough. But you see here, it says that the crate slips backward. So it doesn't slip backward, it slips forward. So we're canceling option B. And then the wind force acting on the crate to make is more, the wind force acting on the crate to make it move forward. That's not true, so it's not the fault of the wind. And of course, we're rejecting option E because option D looks more like the correct answer. Now, this is then question 3. Now, moving on to question 4. We have a truck is moving with a constant velocity on a level road and has a crate in its cargo bed. If the truck suddenly speeds up and the crate does not move against the cargo bed, in what direction is the frictional force that the floor of the cargo bed exerts on the crate? Now, same thing, always try to use quick schematics to illustrate what is going on. This is your truck, this example. And this is the crate at the back. Now here we're saying initially that it's moving with constant velocity on level road. So same idea, so it's moving with constant velocity, okay? So initially with constant velocity. Now, if the truck suddenly speeds up, okay? If the truck suddenly speeds up, what does that mean? Where is the acceleration pointing towards? So lean, the acceleration is pointing forward. Very good. So if it's speeding up, acceleration will be following the velocity. Now, here, in what direction is the frictional force? Okay, well, sorry, we skipped something. Speeds up, and the crate. We're saying the crate and the crate. When the truck is speeding up, the crate does not move against the cargo bed. We're saying if that's the case, in what direction is the frictional force that the floor on the cargo bed exerts on the crate? Now here, we're looking for the direction of the friction, okay? Now, when the truck accelerates forward, what does the crate want to do? When the truck accelerates, yes, Ranim, that's here. Of course, the crate will want to move backward. But we're saying the crate is not moving backward, is not able to move backward. That can only be because of what? Because of friction. And this friction has to oppose the motion or the backward motion. So in this case, the friction has to be opposing the backward motion, which means it's pointing forward. This will be your friction. Okay, so it's moving forward in this case. And you had similar questions in the homework to illustrate the idea. Now, question number 5. So you have a constant force of 170 newtons is applied to a an 82 kilogram crate on a rough level surface at an angle of 20 degrees as shown in the figure and pulled along the surface. Now, if the frictional force F acting on the crate is 37 newtons, what is the acceleration of the crate? Now, we're looking for acceleration. We have a force acting at a certain angle. Now, of course, the acceleration will be only along the x-axis, along x. So I'm taking the positive x pointing to the right, and positive y pointing up. Now, because the crate will be moving only horizontally along x. Yes, Fatima, can you repeat the friction part? You were talking about previous question, Fatima, probably. Right, okay. Yes. So what I may do, Fatima, if you allow me, so I'll probably carry on, okay, with this one, all right? And maybe come back to it when we get halfway through this, if you don't mind, Fatima. Okay, that's great. So we'll get to question 11 or 12, and then we'll come back to that one, all right? Thank you, Fatima. So here we have the action of this force, F, acting at an angle theta, which means if I'm looking at the motion along x, I should consider the x component of this force. So Fx will be the x component of this acting force. Now, what is the x component to be? Is it the cosine or is it the sine? Yes, Lean, cosine. Very good. Tashil, Hana, Mustafa, Fatima, that's cosine. Very good. So it'll be magnitude of force times cosine theta. Okay. Now here, what else is acting along x? I also have this friction. Friction is pointing left, okay, in the opposite direction. And it's also, okay, contributing into this acceleration. Now, I'm going to look at the net force along x, according to Newton's second law, which is equal to mass times acceleration. Then I lay down all my forces. Okay, force cosine theta minus friction. Okay, because it's pointing in the opposite x direction, equal to mass times acceleration. Right, so the rest is easy. Okay, so if you need the acceleration, that's what we're looking for. All you need is take the mass downstairs under the term, you know, the whole thing on the left. So this will give you then acceleration, and the rest is easy. Just plug in the numbers and you get the value of acceleration. These are the steps. Okay, so like I said, divide by the mass, plug in the numbers, you get this value of acceleration, okay, which you can round to 1.5 meters per second squared. I hope it's clear to everybody. Now, next question, a similar question. In fact, it's pretty much the same thing. Okay, perhaps the numbers are slightly different. But we're asking you now for something else. Okay, we're asking you for something else. So the force is now 160 instead of 180, something like that. You have 86 kilogram for the crate. The angle is now 24 degrees. Now we're asking you for the following. Which of the following statements is true regarding the normal force acting on the crate? So now we're looking for the normal. So which means if we're looking for the normal, we need to first look at Newton's second law according to the vertical direction. So according to y. Now remember, y is positive pointing upward. So whatever is pointing up would be positive, whatever is pointing down would be negative. Now, what are the forces acting along y? I have the normal. This is positive, pointing up. Now, the force you see acting at a certain angle theta will also have a vertical component. This is Fy. Now, Fy here will be equal to what? Is it the sine or is it the cosine? It's the sine. Very good. It's the opposite to the angle theta. So it's going to be magnitude of force times sine theta. Magnitude of force times sine theta. And this component, is it positive or negative? Very good. It's positive. Fatima, Tashil, excellent. Why? Because it's pointing up. Okay. And what else is pointing or we can project along y? We have also mg. Now mg, is it positive or negative? Are we taking it positive or negative? So answers, Mustafa, yes, negative, of course negative, because it's pointing down, I'll take it as negative. So that means I'll have normal, okay, plus force F sine theta, okay, minus mg equals to, is the object accelerating along y? The object is not accelerating along y. Do we all agree? So it is equal to mass times zero acceleration. So that means zero. Okay. Now, in this case, I want to know what is normal n. So that means you take everything else to the other side. You end up with normal m equals to mg minus force F sine theta. Now, because we're subtracting this quantity F sine theta from mg, okay? Of course, it's not going to be equal to mg. Normal will not be equal to mg. It will only equal to mg if theta is equal to 0. If theta is 0 degrees, okay, so which means the force will be perpendicular, sorry, will be horizontal, right? Or if there's no force, okay, or if the force is itself equal to 0, then normal will be equal to mg. But for now, no. Normal is not equal to 0, for sure. Normal is not negative, for sure. And normal is not bigger because I'm subtracting here. I'm not adding. So normal is not bigger, is not greater than. So that it can only be normal is less than. Okay? So normal is less than mg. All right? Why? Because again, we're subtracting something from mg. I should get something smaller than mg. I hope it's clear to everybody. Now you have two blocks, okay, of masses 7 kilogram and 9 kilograms connected together by a light string and rest on a frictionless level surface. Now a second string attached only to block B has horizontal force T2 equal 30 newtons applied to it. Both blocks accelerate together. Find the tension in the string between the blocks, okay, T1. So here, okay, now if you notice, I have T2 is acting, it is attached, I mean the string here where tension 2 is acting, all right? So, but tension 2 is acting on the whole system as if it was one big block of mass MA for block A plus MB for block B. So the whole system is acting as if it was one big block of total mass MA plus MB. Now here, which means what? If you look at Newton's second law for this system, net force among X is mass times acceleration. Now, what are the forces acting on this system, MA plus MB? So it's only tension 2. Only tension 2 is acting. We're not considering friction in this case. We're saying frictionless level surface, okay? So if that's the case, so tension 2 will be equal to total mass times acceleration, okay? Now, while we're doing this, we want first to find the acceleration. Remember, the question is, find the tension in the string between the blocks, between block A1 and A2. So I'm looking for tension 1, this tension 1 here, okay? Which is on one side, on the side of block A, it is pulling it to the right, but on the side of block B, it is pulling to the left. You know, the reaction is pulling block, or it has the tendency to pull block B to the left, which means tension 2, okay, is being slowed down by this tension 1. Now, the easiest way would be to find the acceleration first of the system as a whole, and then use this same acceleration, okay, to find tension 1, okay, acting on block A, right? Because in this case, you will know the force, you will know the acceleration of block A, because you see, even though we found an acceleration that is corresponding to both of them moving together, it's still the acceleration of block A when you look at it individually or separately. So that's what we're trying to do. Okay, so let's start with acceleration. So acceleration will be this, will be tension 2 divided by total mass. And you plug in the values, you end up with 30 over 16. Now, having the acceleration, now you focus on block A. Okay, if you focus on block A and you apply Newton's second law, net force along X is equal to mass times acceleration along X. Now, for block A, so all I have is tension 1. Tension 1 now is equal to mass A, okay, multiplied by acceleration, okay, multiplied by acceleration. And of course, because I know the acceleration, and because I know mass A, so it will be 7 for mass A times the acceleration. This is tension 1, don't forget, times acceleration, which is 30 over 16. And we find our tension 1 as easily as that, okay? Right, okay, so this is then, these are the steps similar to what we have just done now. Now, another question we saw either in the lecture, during the lecture, or in the previous review session or sessions we had, okay, related to the apparent weight. So we have a student in an elevator standing on a bathroom scale. When the elevator is at rest, it shows her weight to be 450. Now this is at rest. When the elevator starts to move, the scale shows a different reading. And we all know the answer to this, okay? We're talking about the apparent weight, okay? And the only option that explains what is going on is option B. It says that the scale only reads the normal force between the scale and the student, not the weight of the student. So the weight is when the elevator is not moving, okay? So that's when you get the normal weight. But if the elevator is moving or accelerating, okay? So in this case, if it shows a different reading, that means the elevator is accelerating either upward or downward, okay? So this is the idea here. Right, so I assume this is clear to everybody. Question number 9, I'll probably take a few more minutes from you guys. Sorry, we've been delayed, you know, by the classroom being taken by the engineers. So I'll kindly ask you to give me a bit more minutes. Thank you, guys. So here, a runner of mass 55 kilograms runs at 5.2 meters per second around a flat curved track of radius 300 meters. How great is the force needed to keep the runner on the curved track? Now we're talking about a centripetal force or force perpendicular. It's equal to mass times centripetal acceleration. Acceleration perpendicular. So we have everything we need, okay? So it's a matter of just plugging the numbers. So 55 for the mass, 5.2 for the velocity, and 300 for the radius. You get this much force, okay? Again, straightforward. Now, question number 10. You have a 74 kilogram man and his 16 kilogram daughter stand on opposite ends of a 4.6 meter long uniform wooden plank with a mass of 11 kilograms. Now, if the system is taken to be the man, the daughter, and the wooden plank, how far along the plank from the daughter? So see how the question is being formulated. So how far along from the daughter? That means the daughter is the reference. Okay, so the daughter should be taken as a reference. So how far so how far along the plank from the daughter is the center of mass? So I want to calculate the position of the center of mass relative to the daughter. So the schematic is here. It may not be clear. So the schematic is like this. This is the plank. Let's say this is the daughter here. And this is the father on the opposite end. all right? And we're taking the x-axis as being this horizontal axis. This is the x-axis. The origin is here. So the daughter is considered, according to the question, is the reference point, okay? Now, what are the distances? Now, x, the position x for daughter, because I'm taking her as a reference, will be 0. The position x for the father, xf, will be the length L. So I'm considering L, so I'm showing it here, and I'll show it here too. The bar has a length L, so from daughter to father, so the bar has a length L. Now, if the bar has a length L, okay, what would be the position of center of mass for the plank, the wooden plank, so center of mass here? What do you think? If the total length of the wooden plank is L, so here so L over 2, very good, Faiza, Fatima, so it has to be L over 2. Okay, so sorry, the position of the center of mass. So this is X, sorry, that's not center of mass, XP, let's call it the plank, is L over 2. So I'm still looking for the center of mass, so it's L over 2. Now, I have everything. I'm using the formula X, center of mass, is 1 over total mass, M, sigma Mi Xi. Now, Tanya wouldn't be closer, yes, closer to the man since he's heavier. Of course, we will find in the end, Tanya, that the center of mass will be closer to the man. Okay, so very good. So here, now, if the plank is 4.6 meters, okay, here L over 2 will be 2.3 meters. So here from the daughter to the center, it's 2.3. So I'm expecting to find a center of mass to be closer to the man. Okay, so to find something that is bigger, 2.3. Okay, now let's check that. I'll apply the formula for X center of mass. I'm doing it here. So it's mass daughter times X daughter. Now X daughter is 0. I'll use red to highlight it. So X daughter is 0. So that means you're crossing this term. And then mass wooden plank multiplied by L over 2. Remember, the center of mass for the plank is half the length. And then mass father times X father, and X father is he is at a distance L from the daughter, which corresponds to the length of the plank, and then you divide by the total mass. If you do this, okay, just plug in all the numbers you have at hand, all the numbers, and you end up with 3.6, which does say the center of mass is closer to the man. So somewhere around here, okay? So the center of mass is closer to the man, to the father, okay? I hope it's clear to everybody. Yes. Noor does have a question. Are we supposed to study any questions for chapter 7 in midterms 3? Yes. So you have access also to questions from midterms 3, okay, past midterms 3. So you can practice from those questions. Absolutely. So I made those questions accessible to you guys, okay? So please use them also to review. Right, again, this is question 10. Question 11. The physical quantity impulse has the same dimensions as that of momentum, something we saw already in the review for exam 2019. And it all comes from the formula impulse J is equal to force delta T, or it's equal to delta P, okay, the change in linear momentum. So here the impulse then, dimension of impulse should be the same as dimension of momentum. And question 12, momentum can have the units or the unit of Newton seconds, okay? And it's coming from the same formula, okay? So this is momentum, dimension of momentum is equal to dimension of force times delta T, or you can separate them, force separate and delta T separate, and it's Newton seconds. Okay, so it's Newton second, and this is exactly what we have here. Right, okay, so I'll stop here for now. Now, I may not have answered some of your questions. I think Fatima was asking about what was it again? Yes, the crate here. Yes, question 4, Fatima. Now, for question 4, now guys, if you want to leave, that's fine. You can leave. I'm just going to answer this question and then close the session. All right, guys, thank you very much for attending today, and sorry for taking longer from you. Okay, guys, thank you, guys.
Thank you, doctor. Have a nice day.
Thank you. Have a nice day too as well. Thank you. Yeah, so you are free to stay if you have more questions, guys. So let me then go back to this question. So we said, Fatima, we have a truck like this. 1 second. So this is your truck. And this is the crate on top. Okay, so initially we're saying the crate or the truck is moving with constant velocity, like this, V. Okay. And what happens next is if the truck suddenly speeds up and the crate does not move. Now, speeding up means what, Fatima? Speeding up means acceleration is forward. Very good, right? Now, if the acceleration is forward, what does the crate want to do? Imagine yourself standing here. Let's say you are here standing. If the truck moves, accelerates forward, so you want, of course, to move backward, okay, because of inertia, okay? You want to keep the same slower speed, okay, which means you go backward. And so does the crate. So does the crate. The crates want to move backward. Now, but the question is saying, if the truck suddenly speeds up and the crate does not move against the cargo bed. Now, you see, supposedly, if there was no friction, the crate will move backward like this, but it is not. It is not moving, okay? In what direction is the frictional force that the floor of the cargo bed exerts on the crate? Of course, you know, if you want to prevent this from happening, if you want to prevent the crate to move backward, you need to apply a force that is opposite to this direction. Do you agree, Fatima? Yes or no? Are you with me? Yes. So the only force that can prevent, of course, you're not standing here to pull this crate. So the only force has to come from the surface, and it has to be friction, and it has to oppose, okay, the backward motion. So what is this direction? This direction is pointing forward. Okay, so that's exactly what we have here. Option C is forward. Okay, I hope it's clearer, Fatima. Excellent, very good. Thank you very much then. And yeah, so let's again have another review on Thursday. Okay. In the meantime, I'll be sending some recordings, okay, on the rest of the questions from this midterm 2018 and other midterms eventually. Thank you very much, guys. Have a good day, and see you on Thursday, inshallah. Thank you, guys. Thank you very much.